Okay, so good morning, everybody. So we start today with the TRISEP school with a colloquium. The speaker is Lyons. He was undergraduate at Cambridge, then Oxford do the PhD in Oxford until retirement, and is now emeritus professor at Oxford and visiting professor at Imperial College London. He worked on experiment at CERN, most recently Delphi and CMS, and Fermilab CDF. He was founding chair of the CDF Statistics Committee and CMS Statistics Committee. He wrote the book on statistics for nuclear and particle physicists that everybody knows very well, and initiated the PSTAT series of workshops in 2000 and continued organizing them, and recently I started the PSTAT seminar at CERN too. So today he will talk about what is probability, Bayes and Frequentist approach. So the stage is yours. Thank you very much for being here.
Thanks, Sylvia. So thanks for inviting me. And here's the colloquium. So Sylvia said it's called What is Probability? And we're going to be talking about the Bayes and the Frequentist approaches. So probability occurs in everyday language. I mean, for just some examples, you can ask, what is the probability that it rained in Geneva yesterday? Or what is the probability that signs of extraterrestrial intelligence will be discovered within the next 15 years? Or what is the chance that I will win $1 million or more in the lottery? Sort of a more controversial question is, what is the probability that O.J. Simpson actually murdered his ex-wife? So there are lots of possibilities. Just to show how tricky probability calculations can be, let me tell you about a conversation I had with my barber a few years ago. And we were talking about the lottery, and my barber said to me that he thought of this great way of winning the lottery or improving his chances of winning the lottery. And that was that he realized that the numbers that were chosen by the lottery were chosen at random. And so he had this idea that instead of thinking of likely numbers, he should choose his numbers at random as well, and that would improve his chance of matching the random numbers coming out of the lottery machine. So I tried to convince him that that wouldn't work, but then I asked him whether he would choose the numbers 1, 2, 3, 4, 5, 6, and he told me that's not a good idea at all, because the chance of that combination coming up is really very low. So my reply was that, in fact, yes, it's true, it's very low, but it's no lower than any other specific choice of numbers. And because people think that it's very unlikely, it's quite a good idea to choose 1, 2, 3, 4, 5, 6, because if you win, then it's less likely that other people have chosen that set of numbers and that you will perhaps win the whole of the lottery yourself rather than having to share it with 10 other people. Now, it turns out that actually the combination 1, 2, 3, 4, 5, 6 is the most frequently chosen combination, presumably because enough people know that it's no less likely than any other, and that they want to win on their own. So in actual fact, if you win, you probably would only get a small share of the winnings if that's the winning set of numbers. So the actual conclusion is that my barber was right. It's not a good idea to choose 1, 2, 3, 4, 5, 6. So here's sort of the first slide that I sometimes use when I'm giving the talk with more emphasis on the Bayes and Frequentism. These are sort of two fundamentally different approaches to statistics that I'm going to talk about. It's the subtitle of this is The Return of an Old Controversy. And why do I call it old? Well, in fact, there are two pictures. The one on the left is supposedly Bayes, and the one who was the founder of Bayesian statistics. And the one on the right is Neyman, who played a very fundamental part in the development of Frequentist statistics. Old because Bayes' paper appeared in 1763, and Neyman's sort of seminal paper on the Frequentist approach, it appeared in the year I was born, and I'm not going to tell you exactly when that was. Why controversy? Well, the arguments between Bayesians and Frequentists have been sort of very strong in the past. And it's illustrated in the next slide. This is a slide that I picked up, not actually by looking for slides. It's from the final of the World Soccer Championship. I found it not by looking for football slides, but actually looking through the proceedings of a conference at Nagoya in Japan. It was actually on a very distinctly particle physics topic. It was the CKM triangle, the angles of it, and that was the topic of the conference. One of the speakers showed this slide to illustrate the discussions that were going on within his collaboration between two groups, one of the groups using a frequentist approach to measuring the angles, and the other using a Bayesian approach. And this illustrates the type of interaction that there was between the two groups. So the topics that I'm going to talk about are the following. First of all, we're going to talk about who cares about whether you use a Bayesian or frequentist approach. We're then going to talk about what is probability and the different approaches to it. We'll have the Bayesian approach with some examples. We'll have the frequentist approach, and we'll have a summary. And the discussion is mainly going to be about parameter estimation. There are other topics in statistics like goodness of fit and hypothesis testing, for which these also, the Bayesian and frequentist approach, are also important. But as I say, we'll be dealing mainly with parameter estimation. So it's possible to spend a lifetime analyzing data without realizing that there are these two very different fundamental approaches to statistics, the Bayesian and the frequentist approach. And how does that come about if they're so fundamentally different? And the answer is that in the simplest case that we can imagine of making a measurement, and I'll define that in a minute, both approaches can come up with a sort of an identical statement that the true value of the parameter that we're interested in lies between the measurement minus some specified number of sigma and the measurement plus that number of sigma at some specific probability level, like 68% or 90%, whatever you choose. So the statements can be the same in this simplest case, although the interpretations are going to be very different. What do I mean by the simplest case? I mean that the true value of the parameter can have any value between minus infinity and plus infinity without any constraints, and the measurement is Gaussian distributed about the true value with standard deviation sigma. So these conditions often don't apply. So the Bayesian and the frequentist sort of statements at the end of the analysis could well be different. If you want to read more about this, there's a nice paper by Bob Cousins with the reference given at the bottom of the slide. So we need to make a statement about parameters, the parameters that we're interested in, given our data. And the basic difference between the two approaches is that Bayesians will talk about the probability of a parameter given the data, which frequentists will refuse to talk about for a reason I'll explain immediately. Whereas frequentists speak only about the probability of data given the values of the parameters. That, in fact, is the likelihood function, which my first lecture at the graduate school was about. So here is the what is probability slide. And we will discuss 4 different approaches: the mathematical, frequentist, Bayesian, and the legal probability. The legal probability, I came across, I was looking up, actually, I was trying to find on the web what the technical term Bayesian evidence actually was defined as. And of course, when the word evidence was given to Google, it gave me some law cases. And one of them had a judge summing up to the jury at the end of a trial, which involved, of course, what was the probability that the defendant was guilty. And it was a pretty complicated discussion. So they'd had an expert statistician explaining probability to them. And the judge's summary was, his initial comments to the jury were that we'd had this expert statistician telling us about probability, but he was speaking about mathematical probability. And the judge said, in fact, actually, we're interested in the true probability, not the mathematical probability, and so we can ignore what the statistician has told us. So that's not a very helpful definition of probability. Okay, mathematical probability. This was largely developed by Russian statisticians, with Kolmogorov being sort of very prominent in it. It's a set of axioms about what the numerical estimates of probability have to obey. It's a bit like the basic axioms of geometry, if you like. So there are rules like probability has to be a number between 0 and 1. 1 means that the probability 1 means that the whatever we're talking about is sure to happen. The probability of something happening plus the probability of it not happening has to add up to 1, and things like that. I mean, they're important. They're sort of the underpinning of the frequentist and the Bayesian approaches, but they don't give you a sort of feeling of, at the end of reading the axioms, it doesn't give you a feeling of, ah, yes, now I understand what probability is. So let's go down to the frequentist approach to probability in blue here. So it would be the ratio of the frequencies of the occurrence and the non-occurrence of something that we're talking about, like a certain number coming up when we throw a dice. It's as the number of trials goes to infinity. So you use sort of the probability is just the number of successes divided by the total number. And you're imagining then this repeated identical trials, identical in inverted commas, because I don't mean that you should get the identical result each time you try it, but you're imagining these trials with statistical fluctuations happening from each trial, so that you get a series of possible results. Bayesians actually attack this bit of definition of what probability is, this identical trials, and they claim that you can't decide whether trials are identical enough without using the word probability, but nevertheless, frequentists seem to get by okay. Because it involves these identical trials, it's not applicable to a single event or to a physical constant. So a single event could be like, was it raining? What was the probability that it was raining in Geneva yesterday? And a frequentist would say, well, either it was raining or it wasn't. I don't know, but I can find out by emailing a colleague at CERN. And so it's stupid to talk about the probability of it raining on a specific day at any place. And the argument would be equally true if you were talking about the Sahara Desert rather than Geneva. And similarly, you can't define the probability of the magnitude of some physical constant being in a given range, because there's no repetition of that value of the physical constant involved. For instance, you could, the sort of statement the frequentists won't make is, what's the probability that the fraction of dark matter in the universe is less than 25% of the critical value? So again, we've only got one, there's one true value that we'll eventually discover, and it will be either above or below 25%. Now for the Bayesian approach. The Bayesian approach differs from, another example, by the way, of a single event that you couldn't ascribe probability to would be if you asked, what's the probability that the first astronauts who go to Mars will come back to Earth alive? And, there's only one first set of astronauts going to Mars. So again, frequentists would not have repeated trials and would refuse to assign a probability to that event. I mean, it doesn't mean that the question isn't interesting, especially if you happen to be one of the first astronauts going to Mars, but then you have to find a Bayesian to ask rather than a frequentist. Bayesians, on the other hand, regard probability as the degree of belief that they would assign to some particular event. So it can be applied to a single event or to a physical constant, even though these have unique truths. So if I tossed up a penny and asked you whether it was heads or tails, clearly it's either heads or tails, but you would assign a 50% probability to it being heads or tails. I might have sort of seen that it was heads or tails. I might have had a quick look. And so if I'd seen that it was heads, I would know the probability of that was sort of basically 1. And I mean, there's no sense in trying to assign, from a frequentist point of view, there's no sense in trying to assign probability to it. So you also see that Bayesian probabilities can vary from person to person. Different people can have different views about what the probability of something is. This is illustrated by a story that I heard from the Nobel Prize winning particle physicist Frank Wilczek in a slightly different context, but we can apply it to Bayesian probability. The story is about a workshop on extra dimensions, and there's a young, shy male postdoc who's been attending this, and the sessions are pretty heavy going. So each evening he goes to a pub, sits down at a chair at the bar with an empty chair next to him. He orders 2 glasses of wine and then starts speaking to the empty chair as if there's some beautiful girl sitting there. And he does this the first day, the second day, the third day. And by the 4th day, the barman can't restrain himself and asks, why are you talking to that empty chair as if there's a beautiful girl there? And the shy postdoc replies that he believes in extra dimensions. And it's possible in a 12-dimensional world that there are these really beautiful 12-dimensional girls. And by quantum mechanical tunneling, they could tunnel into our 3-dimensional world, and they have to appear somewhere, and maybe it would be on this empty seat next to him. And then he'd be talking to this beautiful girl, and maybe she'd go out with him. So the barman sort of says, yes, but he continues, if you just look over the other side of the bar there, just sort of 5 meters away, there are 3 beautiful girls there. Why don't you ask one of them to come and sit down and have a drink with you? And the postdoc replies, oh, there's no point in doing that. That would be very unlikely. So you can see that different people can have different perceptions of what's likely and what's not. So you might at this stage wonder how Bayesians can actually calculate anything and how they ascribe numbers to things. And the idea is that it's quantified by a fair bet. And the fair bet is that if the Bayesian believes that the probability of something happening is 20%, he should be willing to offer odds of 4 to 1 to somebody to bet on that against him, or 1 to 4 to bet in the other direction. And if the Bayesian assigns the incorrect probability, he or she stands to lose money. So that's supposed to keep the Bayesians honest. Another illustration of Bayesian probability is if we go back to the picture of Bayes at the beginning, at the top left here, this is the only picture of Bayes that exists. And the problem is that many experts on the history of science don't even think it's a picture of Bayes. They think that the clothing that he's wearing is not typical of that period. And so here in relation to the picture of Reverend Bayes, we cannot, it really is possible that it isn't Bayes. So the probability that this is actually a picture of Bayes is certainly not Frequentist probability. And in fact, the probability of Bayes is Bayesian probability. So I think that's quite amusing. Okay, so now down to a bit of work. We are going to need the concept of conditional probability for the sort of talking about Bayes and Bayes theorem. So we have the conditional probability of A, given the fact that B is happening, which is written like this, or with a semicolon between A and B. It's the probability of A, given the fact that B has occurred. So if you have this sort of Venn diagram representing measurements of numbers of occurrences of things, then the outer rectangle represents sort of everything. The red ellipse represents the number of times that A has occurred, and the blue ellipse is the number of times B is observed, and then this funny shape, sort of like a bit like a moon, a bit more than a quarter moon or something, that's the number of times that A and B occurs. And you can quickly convince yourself by considering the probability of A and B both happening, that's the number of occurrences in that funny region, it's equal to the probability of A happening, given the fact that B has happened, times the probability of B. So that's our basic formula for the fact that A and B have both happened. If you want to go back to a formula that you would remember, perhaps even from your school days, if A and B are independent of each other, this probability of A happening, given the fact that B has happened, is just the probability of A. And then you get this famous formula for for independent events, that the probability of A and B both happening is equal to the probability of A times the probability of B. If we are dealing with independent events, then we should apply this formula. So if you ask at the end of the year, if I select a random day, what is the probability that it was a rainy Sunday? And the probability of it being a rainy Sunday, rain and Sunday are uncorrelated with each other, although it seems to people have the perception perhaps that it rains more at weekends when they're off work than during the week, but not true. So the probability of a rainy Sunday is equal to the probability of the day being rainy times 1/7. That's because they're independent. But if you change it a bit to ask if it's a rainy December day, then it's not equal to the probability of any day during the year being rainy times the 12th, because rain and winter in most places are correlated with each other. So they're not independent. It's not equal to that sort of product there. And similarly, if you have a beta decay, you can ask what is the probability of the electron energy in a beta decay being larger than average, say, and the probability of a neutrino being larger than average? And the answer is it's 0, because the total energies have to add up essentially to the total energy available. So it's not equal to the probability of the electron energy being larger than average, which is about a half, times a similar half for the neutrino, again, because they're not independent. So, okay, now we're going to do Bayes' theorem. It's this green formula here, the probability of A and B equals, that's the probability of A given B times the probability of B. That's just this blue formula up at the top of the page. But we've extended it by noticing that the probability of A and B is the same as the probability of B and A. And so we can replace A's by B's and B's by A's, and we get the probability of B given A times the probability of A. And then Bayes' theorems, it's usually written down as the second equality here, where we've divided through by the probability of B, and it's the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. And it relates these two conditional probabilities, the probability of A given B and the probability of B given A. So usually these two probabilities are not the same, and we'll have examples afterwards which illustrate that's not true. If you just look at this diagram for a moment, you can see for yourself after a couple of minutes that the probability of A given B is not equal to the probability of B given A. So this theorem is completely uncontroversial, by which I mean not only Bayesians would believe in it, but Frequentists as well, provided that, and the ... that you're supposed to fill in for yourselves is provided that these probabilities are all genuine, allowable Frequentist probabilities, then Frequentists would believe in it as well, whereas Bayesians believe in it for Bayesian probabilities. I mean, if they're not Bayesian, if they're not Frequentist probabilities, the formula sort of doesn't exist really. Okay. So, okay, this is again examples of conditional probability that we don't have to go through. So here's Bayes' formula written again in this purple rectangle. And where does the controversy come in? The controversy comes in when A is replaced by a parameter value and B is replaced by the data. And as I've said before, Frequentists will not talk about the probability of parameters having specific values. So here's the formula written out by sort of with this substitution. So it's relating the probability of a parameter given the data to the probability of the data given the parameter times the probability of the parameter. So what are these different terms here? The probability of the data given the parameter, that is the likelihood function that you got from analyzing your experiment. The probability of the parameter here is known as the Bayesian prior, and it's what you knew about the parameter before you did your measurement, maybe from previous measurements, maybe from some theoretical argument. And then this is what you know about the parameter after you've done your experiment, and it combines your new information with the prior information. It updates the prior using your likelihood to give you the posterior. Just one little story about the nomenclature here, a story that I got from a Bayesian statistician from Duke University, Jim Berger, and he tells the story that he and his wife have professions that are very similar, except for one small difference. And he's a Bayesian statistician. His wife is a fitness trainer. So what is the similarity between these two? And he says that they're both involved in optimizing posteriors. And the difference between the two is that he is trying to maximize the Bayesian posteriors for his client, where his wife is trying to minimize the posteriors of her clients. So maybe that helps you remember the terminology a bit. So what are the problems for the frequentists? Well, the crucial problem is, as I've said, you're talking about the probability of a parameter sort of here on the right-hand side, and the prior and the posterior and the other side. So frequentists would say, Bayesians would say, well, that's no problem. It's just because frequentists are using this very restricted definition of probability. And we are talking about degree of belief. The next problem is, what do you put in for the prior? So it's probably easy if you've got previous measurements that are relevant, because then you would put in, say, a Gaussian distribution centered on the central value of the previous measurement, and with a width corresponding to the uncertainty of the previous measurement. But sometimes you're doing really frontline measurements in a situation where the previous measurements are either non-existent or very much worse. And you still, in order to use the Bayesian approach, you have to put in something for the parameter here, the prior. What do you do when you've got no information that's terribly relevant? You might imagine you'd use an uninformative prior. An uninformative prior, for instance, could be flat in the parameter, then that does not favor one value of the parameter with respect to the other. That sounds quite good, but then you begin to think about it, and you begin to have doubts, because, for example, if you're measuring the mass of the lightest neutrino, then and you're measuring it much more accurately than anybody has ever done it before, then what do you put in for the prior? And are you going to make it flat in the mass of the neutrino? Or maybe the mass squared is a more relevant variable. And log mass seems to have attractions as well. And not only are you ignorant about the mass, you're also ignorant about the mass squared and the log of the mass. And flat in each of these three variables is different. So you're going to get three different answers if you use these three, and maybe there are more priors as well. So that's a problem. And things get worse if you're measuring several parameters at a time, because then you need a multi-dimensional prior. So how do you ever get a sensible answer from a Bayesian analysis like this? Well, it's unimportant if you're in a situation where the data overshadows the prior. So what do I mean by that? Well, here's a sort of sketch of the results of measurements from the LEP collider, the E+ collider that was in the Hadron Collider tunnel before it became a Hadron Collider. And it was measuring the mass of the Z boson. And there were 4 collaborations, and when they combined the results, they got an answer of not exactly, it was 91,188. But here it's more or less 91,000 MeV with an uncertainty of 2 MeV. So this is distinctly a broken scale here, because this uncertainty is only 2 parts in 10 to the 5th. So it's a very narrow peak on a sort of really linear scale. So this would be the likelihood function from the measurements, sort of Gaussian, centered on 91,000 or whatever, and with plus or minus 2 MeV. And you have to multiply this by the prior to get the posterior probability. And the point is that over this small mass range, pretty well any prior that you choose, whether it's flat or 1 over the mass or 1 over the square root of the mass or even proportional to the mass, they're all essentially constant over the relevant range for the likelihood. So you multiply this Gaussian shape by a constant, which is pretty easy to do, and you end up with a Gaussian shape for the posterior. So this is a situation in which you have almost no sensitivity to the prior whatsoever. But it's worse if you have a signal that's wide, that has a large width compared with its sort of numerical value. So maybe here, this is an experiment to measure the production of some fairly rare process. And what we're plotting is the likelihood as a function of the signal rate. This is what we get from our own measurement. And here, it looks as if the answer is a Gaussian for the likelihood, centered on about 3, whatever these units are supposed to be, plus or minus about 1. And now to get to the posterior, we multiply by a prior. Now, if we choose a constant prior, we end up with exactly the same shape as we have for the likelihood. Whereas if we have a prior that goes like 1 over the signal rate, you can sort of imagine multiplying in your head these two functions, and you can see that you're going to enhance the posterior will, as compared with the likelihood, will have the lower side enhanced and the upper side depressed a bit. So you get this thing skewed down, and any sort of estimate that you make, like the peak of the posterior, will be down compared with the peak of the likelihood, whereas here they'd be in the same place. So now we have sensitivity to the prior, and it would be even more significant, the difference between these two priors, if we had the likelihood really peaking closer to 0, or even wanting to peak at a sort of negative value. And so we're going to be in a situation where we're just calculating an upper limit on the process rather than quoting a central value plus or minus an uncertainty. So it really is important, if you are doing Bayesian analysis, to state what priors you're using. Now, here's a case where arguably the Bayesian method is quite nice, and that is talking about the mass squared of the lightest neutrino in beta decay. It turned out that over the past 20 or 30 years, until the last few years, all measurements of the mass squared of the lightest neutrino turned out to be negative. That's negative mass squared for the best value. And they turned out to be about 2 standard deviations below 0. So as the experiments got improved accuracy and the standard deviation went down, the actual value would get closer to 0, but they'd all be about 2 standard deviations below 0. Here I've attempted to sort of draw that with the likelihood function. Likelihood in inverted commas, because you're not really supposed to calculate a likelihood for negative mass squared. But nevertheless, it would sort of look like that. I've drawn it as about half a standard deviation below 0, so you can see the tail out here a bit more. So what is the Bayesian approach now? This is the likelihood from the measurements. what do you do? You multiply by the prior in order to get the posterior. What prior would you use? Well, in the negative mass squared region, you might well set the prior equal to 0. That's supposed to be at 0, but I couldn't draw a red line. My computer wouldn't let me draw a red line on top of a blue one. So you'd set the prior to 0 in the negative region, and you would set it to non-zero, and I've just drawn it as a constant at positive mass squared. And now you have to, the posterior is now obtained by multiplying the prior by the posterior. You get 0 for the product out here, and in this part of the distribution, the shape is unchanged by having a constant there. And so the posterior that you end up with is 0 at negative mass squared, and then as shown for the likelihood function at positive mass squared. So that way you will ensure that your optimal value is a physical, it's not a physically impossible value like we were getting here with negative mass squared. And with 2 standard deviations down, your upper limit that you get on the mass squared is dangerously close to being negative as well. But whereas here that will never happen. Disadvantages of this approach? Well, if you really think that maybe the neutrino is a tachyon, then it's a mistake to put the prior 0 at negative mass squares. You'll never find a tachyon this way. And the other thing is that if you come to average a lot of different measurements, which are sort of really should be close to 0, some are negative and some are positive, then you will get a biased value if your procedure basically leaves positive mass squared results as they are, and negative mass squared results are forced into the positive region. So even though they're really scattered equally, sort of above and below 0, massaging the negative mass squared ones is going to give you a biased result. Okay. So here's a plot produced by Ilyanovsky at the Fermilab Phi-Stat meeting in the year 2000. It was Confidence Limits Workshop, it was called then. What it is showing you different Bayesian priors and different other methods of calculating upper limits. In a Poisson counting experiment, for instance, an underground experiment running for a year looking for WIMPs, and the estimated background from whatever sources is 3.0 events. And then you run for a year and you find that you have observed some number of events, and here are the different possibilities here, going from 0 to up to 6 and so on, but you could continue larger. And then what is plotted is the upper limit that you get on the signal process above the background when you observe 6 events and the background is 3. And what you see is you get a whole series of answers that range from about 6.5 up to 9.1. The range of values is even more impressive when you come down to a situation where the observed number of events is smaller than the estimated background, which can happen by fluctuations, because here, if you observe only 1 event, the different methods shown go from about 0.3 up to 3.3. So that is really quite a range. So it's not like asking the question, what is 2 plus 3, where there's one very preferred answer. Here, there are a lot of answers, each of which are valid within the assumptions that are made, but are different. The moral of this is if you quote an upper limit on the flux of WIMPs through your detector, then you should be very careful to specify what the statistical procedure was that you used to extract the upper limits. this probability of A not equaling the probability of B, it sort of confuses a lot of people. And so here's an example that is supposed to help you understand the difference. So A and B are going to be data and theory. So the probability of data given theory is not equal to the probability of theory given data. Now, what we imagine is we have a database containing sort of everybody in the world, and we have two pieces of information about people. One is a sort of theoretical parameter, if you like, that is whether they're male or female. And the second one is a piece of data, and that is whether they're pregnant or not. So what is the probability of data given theory? What is the probability of, if you pick a random person from this database, if they're female, what's the probability they're pregnant? Well, it's about 3% for a random female at a random stage in her life. Okay, now you pick somebody else out of the database, and it turns out this person is pregnant. So what is the probability of flipping these two around? What is the probability of the person being female, given the fact that they're pregnant? And that is very much bigger than 3%. So if you sort of flip into the idea that these two have to be equal to each other, this is an example that I use for myself to remind myself that that's not so. Okay, I think we have to leave out this interesting story about the peasant and the dog, unfortunately, because of time, and we ought to go over to the Frequentist method of measuring things. So the Frequentist method is due to Neyman, and the Neyman construction is an idea that can be applied to pretty well any measurement and to extract the parameter for it, if you've got enough information. And it uses only the probability of data given the parameter. It does not talk about the probability of a parameter, because the Frequentist method doesn't allow you to do that. And you end up with a confidence interval going from mu1 to mu2. And the way it works, we'll come back to this slide in a minute, is the following. So here is a plot of theoretical parameter going up there, observation going this way. I don't like thinking just of abstract quantities. So I'm going to imagine this is the temperature of the thermonuclear reactor at the center of the sun. And this is the observation of the neutrino flux from running for a short while, like a month, one of these big underground detectors like SUperK. And the way this plot is constructed, the plot shows you the sort of like the most likely values of the observation given any value of the theoretical parameter, the temperature of the sun. So if the temperature of the sun in unspecified units is 6, what you assume you can do with some difficulty is to calculate at every possible observation rate going across here, what is the probability density of getting that particular value of the observation, for which you have to know a lot about nuclear reactions at the center of the sun, convection in the sun, neutrino propagation through the sun, possible neutrino oscillations as they come between the sun and the earth, a lot about your detector as well. So you need an awful lot of knowledge. But then what you do is you construct a region, say a 90% region, a region that contains 90% of the probability of this distribution all the way across here for all possible values of x. So you do that for the value 6, and then you do it at all other possible values of the temperature at the center of the sun, going down to 0. We will not go down to negative temperatures at the center of the sun because they're meaningless. And then this band is the confidence band, which tells you likely values of the observation for the specific values of the theoretical parameter. And then you actually run your experiment. You can do all that before you do the experiment, except you probably need the experiment to tell you some features of the detector that you need in this calculation here. But anyway, you then run the detector for a month, and the value of the flux is 3.1. And then this enables you to say that for values of the temperature at the center of the sun between 1.5 and 3.2 in whatever units, for values of the temperature in that range, this would be a likely observation. If I thought of a temperature outside that range for 6, all the likely values are higher than I observed. And if I thought of a temperature of a half, all the likely values are lower than the ones that I thought. So that is how you extract the range for the parameter. If you're listening really carefully, you will have noticed that I said that this was a 90% region rather than the 90% region, because there are lots of 90% regions I could have chosen. I could have chosen a region which went from x equals infinity to a little bit to the right of the lower boundary, which also is a 90% region. And then instead of having this bend, I would have covered over a big region of this plot going to the right of some other curve just inside where the boundary here is. And that would have been useful if I only wanted to calculate an upper limit on the temperature of the sun. And I could correspondingly have had a lower limit, and I can sort of have disjoint regions that add up to 90% that probably would be useful for nothing at all. Or I could have a different ordering rule for collecting these things that would give me what's known as the Feldman-Cousins procedure for unified limits, which is quite important, but I'm not going to talk about now for lack of time. So that is how the Frequentist method works. And here it sort of says it gives a range of mu for which the observed values, the observed value from your experiment was likely. At least that's a true statement for the central range that I was showing. The range that I was showing imagined that you had 5% here and 5% out there and 90% in the middle, the so-called central interval. Okay, so here we contrast the two statements about that the Frequentists and the Bayesians make, that mu, our theoretical, our parameter that we're interested in, lies between mu lower and mu upper at 90% confidence. So for the Frequentist, mu lower and mu upper have been measured in our experiment by the Neyman procedure. And so mu lower and mu upper are known, but they're regarded as random in the sense that if I repeated my experiment because of fluctuations, I would have got a different range for mu. So they're regarded as random, even though they're specific values from the measurement. And mu is unknown, but it's regarded as a fixed value. That's in truth, it has a fixed value, and it's just that we don't know about it. And so this is a probability statement about mu lower and mu upper. The probability statement, if we repeat the experiment again and again and again, I would expect, using this procedure that I've described, I would expect that 90% of them would contain the true value of the parameter, assuming the experiment has got no biases that you don't know about. The Bayesians have a very different interpretation of this experiment. They say we've measured mu lower and mu upper, so they're known, and we're not going to consider what happens if I do something different, if I repeat the experiment again and again and again. I just going to concentrate on these specific values of mu lower and mu upper. Now, the true value is unknown, And as a Bayesian, it's treated as a random number that has a probability, a credibility, Bayesian credibility distribution. And so it's a credibility statement about the posterior probability distribution for mu, that 90% of this probability distribution lies between mu lower and mu upper. So they're very different in what they regard as fixed and what they regard as variable. So this is just the idea of coverage that the Frequentist statement is about. Here is sort of a plot with an axis showing mu, and this is the true value, which of course we don't know. But the idea is that if we repeat the experiment again and again and again, these values sort of shuffle around, and 90% of them would cover the true value here. That's the idea. Okay. So I think it's time to draw to a conclusion, although there are many interesting other things we could have spoken about. And so here's a little table that shows you that compares and contrasts the two different approaches, the Bayesian and the Frequentist approach to statistics. So the basis of the method is, if you're a Bayesian, it's Bayes' theorem, and you derive the posterior probability distribution from your data, whereas the your data and the prior. Whereas the Frequentists use the probability density function for the data for fixed parameter values. What is the meaning of probability? Well, it's degree of belief for a Bayesian, and for Frequentists, it's not surprisingly the Frequentist definition of probability. Are you allowed to speak about probabilities for parameters being in certain ranges? Yes, yes, it's a statement of what I believe about the parameters, and I can have opinions about that. Whereas for Frequentists, it's very much no, 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 don't speak about the probabilities of things for which you cannot possibly have repeated samples. Do you need a prior distribution in order to carry out your procedure? Well, yes, you definitely do for the Bayesian approach, and no, you don't for the Frequentist. There is no prior involved in the Frequentist approach, primarily because you're not allowed to speak about the probability of a parameter. And that is a big advantage for the Frequentist method, because you can have a sensitivity to the prior. Do you have a choice of interval? That means, can you get central intervals, lower limits, upper limits, whatever? And the answer is yes. You can choose, once you've got your Bayesian posterior probability distribution, you can sort of divide out some 90% region, whatever where you want. And for the Frequentist method, yes, again, you can choose, as I explained by looking at that plot of the Neyman construction, you can choose whether you get a central interval or a lower limit or an upper limit or whatever. And the only case in which you cannot choose what sort of limit you get is in the Feldman-Cousins approach, because it chooses the range for you, and it sort of flips continuously between a lower limit if you have a small observation and a two-sided interval if you have a larger signal. What data do you consider? And the Bayesian approach, it's only the data that you have, whereas in the Frequentist approach, it's the data that you have plus other possible data. And that's somewhat of a disadvantage, because you have to sort of imagine what other possible data you might have had, whereas the Frequentists have the advantage of only using the data that you've got. So this is essentially saying the same thing again. You need an ensemble of experiments, no for Bayesians and yes for Frequentists. What is the final statement that you come out with? Well, really, Bayesians like to come out with the posterior probability distribution. They would say that's the end point of their analysis. I mean, for the purpose of quoting numbers in the abstract or conclusions, they will sort of extract upper limits or two-sided intervals from the posterior probability distribution, but this contains more information. Whereas the frequentist method, the final statement is the parameter values for which the data is likely. So that's not what you might have been thinking would be the most interesting thing to deduce from your experiment. You'd like to know probably the probability distribution for different values of your parameter. But this, again, I repeat, is the parameter values for which the data is likely. Can you get unphysical regions or empty regions? Well, you can exclude those by the prior, as we were talking about for measuring the mass squared of the neutrino, whereas in the frequentist situation, they can occur, which can be slightly embarrassing. What about systematics, which is a very big subject, which I have not mentioned? The way you include systematics in a Bayesian approach is that you regard them as you represent them by nuisance parameters, and they're just another parameter in your overall fit. And then you integrate over the prior for these systematics and you extract your final answer. Whereas the frequentist method, if you want to do it really in a pure frequentist method, you have to extend the dimensionality of your frequentist construction. And that quickly becomes quite cumbersome and computationally intractable if you've got more than about 3 parameters. So that it's easier in the Bayesian approach to integrate systematics. Coverage, this property of if you're aiming for 90% probability, do you get 90% probability from the method that you're using? And the Bayesians would say, well, it's not, you don't necessarily in the Bayesian approach, but the Bayesians would say it's unimportant because coverage is a principle, is a concept which applies to extra measurements that you might have made, and how many of them would include the true value of the parameter. And that is not something that Bayesians want to do. They want to consider just the data that you've got. Whereas for frequentists, the coverage for the Neyman construction, it's built in. You're guaranteed that you will never undercover, which is quite a nice property. And finally, there's decision making, which I haven't spoken about, but the question is, after you've done your measurement, what do you do next? You tear out the LEP collider, the E plus E minus collider, and replace it by a hadron collider, or do you run LEP a bit more to see if you can find the Higgs there? And the answer is that the Bayesian approach is set up for this quite nicely. You have to incorporate a cost function for the possible outcomes, whereas the frequentist approach, which is only telling you parameter values for which the data is likely, it doesn't have immediate access to decision making. So to sort of really sum up, first of all, there's the cynic's view of the Bayesian and frequentist approach. So the cynic likes neither of the approaches because he says that the Bayesians address a question everybody is interested in. What do you believe about different values of the parameter? How probable are they? So they're addressing that question by using assumptions nobody believes, namely the priors that caused a lot of trouble. Whereas frequentists use this really beautiful logic of the Neyman construction to deal with an issue which is of no interest to anybody. They're just talking about what are the values of the data for which what are the values of the parameter for which the data was likely. And people want to know more than that. So that's the cynic's view. On the other hand, the approach used at the Large Hadron Collider is that people are recommended to use both Bayesian and Frequentist approaches. And if they agree, then everybody is very happy. And if they disagree, it could be because they're asking slightly different questions, could be because there's a bug in the program. It's worth further investigation. So we've come down in favor of both of them. Anyway, my conclusion at the end of this talk is I hope you have an understanding of the Bayesian and Frequentist approaches. And if anybody asks you to explain the difference, then probably you'd be able to provide them with a good explanation. So thanks very much, and sorry I overran a bit.
Thank you very much. Very nice colloquium. Great. Are there any quick question? If not, we would need to go to keep continuing the. So I see one in the chat on slide 23. Is it possible to combine these different results obtained by different data analysis approach into the final optimized result?
Oh, you mean to combine a Bayesian approach and a Frequentist approach?
On slide 23. Alan, you can.
23,
yes.
Okay. It's sort of ignoring a lot to combine a Bayesian and a Frequentist measurement. I guess that the particle data group, when they combine values, really sort of don't pay all that much attention to whether what the method used was. And in a sense, the slide that I showed of the football match at the beginning showed that people were at least comparing Bayesian and Frequentist approaches. So you can do it. Part of the series of talks that I gave to the graduate students included combining results. And the first message there was that it's much better to combine the data, to go back to the data, even if both of them are using a Frequentist approach or both of them are using a Bayesian approach, go back to the data and combine that. That's much better. So yes, I suppose you could, and people do the combination of Bayesian and Frequentist approaches, but it's a little bit dodgy. Did I understand the question correctly? It's not quite connected with slide 23.
Yes, it seems that you understand the answer correctly. Thanks. There are other few questions. I'm not sure if we can go with the other question. Just looking for the TRISEP people, if we can have some time. Chris, Erika, could you comment about that? Can I go with the other question?
Why don't we join the other? We'll join the regular TRISEP school at 11:15. And we'll take questions until like 11:14:30, and then everyone will switch over.
Okay, so there is another question from David. Question about flavor physics. How does one determine when, if we are seeing signs of new physics from indirect measurement, be anomalies or G-2?
Yeah, okay. So G-2 has been in the news, big news recently. I listened into the seminar given from Fermilab that was open to the general public. And the comments by people from the general public were really quite interesting. Like, I didn't understand a word of it, but it sounds really exciting and things like that. Okay, G-2 is quite interesting because there's a recent calculation. I mean, you're comparing the experimental value with a theoretical value, and there's recently been a recalculation of one of the corrections, one of the many terms contributing to the theoretical value, which makes it much more consistent with the two measurements. So that's a real problem to decide what to do. You've got the experimental value, possibly combined with Brookhaven, they're nicely consistent. And then you've got two values of theory, the sort of traditional value that people have had for the last few years, which is discrepant, and then a recent lattice calculation, which is like 1.5 sigma away, which is not very significant. I can sort of avoid the question by saying this is a physics question rather than a statistics question. But yeah, what statistics is going to do for you is to say, is data consistent with the theory or not? And now, if it isn't, then either the experiment could be wrong, or the theory could be wrong, or both of them could be wrong, or it could be a big statistical fluctuation. You really don't, you're not really testing a specific alternative hypothesis there. This is really like testing just the null hypothesis, that it's just the physics that we know, and you're getting the answer. If you take the old calculation, you're getting the answer, they don't agree. So if they don't agree, it means it's not just traditional physics, it's something else as well. So that could be signs of new physics, provided it's not something wrong with the experiment. So yeah, these sort of virtual effects are hard to interpret, and there are many possibilities. And I think it's as far as the agreement or disagreement goes, it's watch this space, especially on the theory side.
And thanks. And then there is another, I saw the video of David popping up. I'm not sure if he wants to comment. Maybe not. And
No,
so,
I just, thanks a lot. I just didn't know if this was whether you would get a different, whether statistics could say anything about this. But you're saying no, it's really just a comparison of theory and experiment.
Yeah, statistics is saying that could say something like they're discrepant, and the probability of this being a statistical fluctuation is something. And now it's up to you to decide what you do with that information.
Okay, thanks.
and then there is last question from Ryan, whether it can a frequentist accommodate a prior by adding a penalty term to the likelihood function? And isn't that ultimately equivalent to a prior from a measurement?
Well, yes. I mean, that's the way frequentists will allow for systematic effects by having a nuisance parameter and including a term in the likelihood that allows for that. So basically, you're imagining there's some subsidiary experiment going on, and that contributes to the likelihood. But the interpretation is that, again, you have a frequentist interpretation of that, and that is that that extra term is a function. You've got your data, and you have this extra term which sort of restricts the nuisance parameter, but what it's doing is it's doing much the same thing as it would be if that measurement had been part of the main experiment. So that extra penalty term is looked at in a frequentist way, rather than as a Bayesian way, that the nuisance parameter itself has a spread in values. I think I haven't explained that very well, but that's the essential way of looking at it. And I mean, there's another approach of accommodating nuisance parameters that I haven't mentioned, and that is the Hyland-Cousins method. And that is actually a mixture of a frequentist and a Bayesian approach. It's sort of frequentist in the main measurement, and it's Bayesian in the way the nuisance parameters are treated. Bob Cousins says that on Mondays, Wednesdays, and Fridays, he's very happy with this practical method of dealing with nuisance parameters, which doesn't seem to do too much harm to the procedure. And on the alternate days, he's sort of very embarrassed that his formula for sort of probability of whatever is a mixture of Bayesian and Frequentist probability at the same time, which doesn't make sense. So you can sort of be pragmatic and try and do that. But in general, the idea would be that the extra nuisance parameter would be regarded in a frequentist way. I should also say that in general, we would not be doing a full Neyman construction in many dimensions, because it's too, you've got loops within loops in your Feldman-Cousins software, and it becomes too difficult. In the original paper, they spoke about a situation where you had two parameters. It was for neutrino oscillations, and the two parameters were sine squared 2 theta and delta m squared, and you could get by with that. But if you go beyond that, it really is very difficult. And what the usual procedure to do is just to use the likelihood function, which is sort of intermediate. It's sort of, I would regard it as neither Bayesian nor Frequentist. Other people call it a sort of Frequentist method, but it doesn't have the property, for instance, of the Neyman construction that it guarantees coverage.
Okay. Thank you very much for the great colloquium. Thank you.